Our final research presentation, last but certainly not least, is by Evan Warrens from Boston College. And Evan will be presenting about producing a landfill simulating bioreactor, some of the considerations, design, and impact. So I will turn it over to Evan.
All right, let me share my screen here and we can get started. Everybody can hear me all right? We're good? Okay, awesome.
Yep, loud and clear.
Awesome. Okay. So, all right. So, a little bit of an intro. My name is Evan Warrens. I'm from Boston College. I've been working with DL and Dr. Julia DeVoy on this project since 2020. I've also worked with a lot of other fantastic people who have worked to, bring this whole project together and also make this conference a reality. So I just want to thank everybody that I've worked with so far. It's been a great experience. And so my presentation here is going to take a bit of a narrative approach, kind of talking about our project, how it's grown over time, how this idea of a landfill simulating bioreactor came from a question and a problem that we had, and then developed into kind of this bigger expanding project. So as any story, good story will start off with, we have a problem. And if this picture to your right and kind of all the legwork that's been done so far by DL and Amy and Ragul and everybody else here hasn't tipped you off to what that problem is it's the issue of textile waste. So right now, a lot of societies, especially Western societies, like in the US, have this issue with fast fashion, where clothes are being produced faster and cheaper than ever, which creates people having more clothes than they need. US alone produced 34.1 billion pounds of textile waste in 2018. And only 15% of that, as Ragul has just stated before, was recycled. So obviously there's this huge gap between clothes that are produced and clothes that are actually, being able to live their full production life cycle. And so when those aren't being recycled, they're being put into landfills, they have to go somewhere. And really robustly, we can use things like UN data, UN Comtrade data to track where these clothes go. And so one of the issues, though, is if we have all this great data on where the clothes go, they're leaving places like US, South Korea, UK, Japan, and Germany in billions of pounds per year. And they're ending up in places like Tunisia, Ghana, Nigeria, South American countries like Guatemala and Chile, and even Middle Eastern countries like Pakistan and United Arab Emirates. So what happens to those, to that clothes after they kind of enter those countries? So there's not really a lot of data on the impact of what one article of clothing releases to the environment. And that would be something that's very useful to have, because if we can figure out that 34.1 billion pounds of textiles are entering the waste stream, if we can figure out the weight of 1 pound or one article of clothing, we can kind of extrapolate that out to the total mass and get a better estimate of the problem. Oh, and so there's my little graphics there that I mistimed, but going from one shirt to the bigger pile. So kind of intuitively, why is this a problem? Why do we want to care about this and figure this out? We don't really know exactly the impact of a piece of clothing being entered into the environment, but we can assume that it's not going to be good, right? Anything synthetic that we put into the environment, we can assume it's not going to be good. And as DL introduced earlier, there is kind of this issue of waste colonialism, where countries in the West and in the global North are kind of offloading their waste onto other countries that don't exactly have the same amount of resources to prevent this happening. So when they enter those other countries, there's a lot of negative impacts. There's impacts on local textile workers who are kind of losing work and business from being swamped with these cheap secondhand textiles. And there's also clearly the issues of contamination from waste. So we have, this is an image here from a landfill fire that took place in Ghana a couple of years ago. It was the Capone landfill fire. And this was kind of massive and burning and releasing, who knows what kind of pollutants into the environment. And so even if there isn't some catastrophic fire like this, there's still adverse environmental impacts, right? So there's chemical leachate coming off the rainwater that filters through these shirts. Just thinking about the dyes and treatments and metals that are being put into those shirts going back to the groundwater can't really be very good. And there also is the generation of greenhouse gases like CO2 and methane, not just from incineration in fires like these, but also just in biological degradation. So in the US, a lot of times, and in other Western countries that have highly engineered landfills, there's kind of tools and resources to prevent these chemical leachates and greenhouse gases from going into the environment. And even sometimes there's technology put in place to kind of collect the greenhouse gas and be reused for power. But in a lot of other countries that are being negatively impacted by this textile waste dumping, they don't have access to the same like highly engineered landfills. So a lot of times they get put out into these open air dumps that are more exposed to fire and pollution. These are some more images. So with that kind of problem identified, that we need to be able to quantify the amount of textile waste so that we can spread awareness on this issue and get kind of the ball rolling on solutions, we decided that we need to find something that can measure this. So we looked to some previous research, and we looked at this paper by Zhang and Townsend, the effect of waste depth on leachate quality. And we saw this fantastic landfill simulating bioreactor, or this waste leaching lysometer that we thought would kind of be perfect for our purposes here. They use this to measure construction debris, and we figured that we could kind of replace that construction debris with textile waste and get the same kind of impact that they did. But there's a little bit of a problem here. Yeah, most bioreactors or lysometers are huge, either requiring a dedicated spot outside or taking up basically an entire lab space. And they're also generally incredibly expensive. And so those both were kind of luxuries that we did not have the ability to overcome at the time. So we kind of thought, well, just continuing through examples of some of these earlier ones. This initial one is, I think it's about 6 feet tall and 1 foot in diameter. This one, again, I think was about the same height. And I thought it was funny that they had to put it on wheels to get it to move it around if they ever needed to bring it somewhere else. That's how big it was. A lot of them are also just getting incredibly complex here. Like there's 6 different pumps. I don't even know what's going on. Again, another super tall one, highly engineered, and it's great. And these are all fantastic. And a great place for us to start, but we just did not have the space to kind of have a 130 liter, 6 foot tall landfill simulating reactor. A lot of interesting and unique kind of ways that people thought about avoiding this. So this one was focusing on the effect of waste depth. So to kind of simulate waste depth, they had a series of, I think they were 1 foot tall lysometers in a row. When you put 6 in a row, you can simulate 6 feet of depth. So it seems like other people have encountered these issues of volume before and have come up with some unique ways to get around it. So we figured that we could just kind of do that ourselves too. And here's an example of one of these series lysometers in functionality here, how it would actually look like in a lab, again, taking up a lot of space that we didn't exactly have. More just super complex drawings here. And okay. So can we design one of these to fit our own needs, kind of like how other teams have before? And the answer that we came up with was, why not? You know, we may as well try. Like any good researchers, we decided to kind of take that into our own hands. So first, we kind of have this overarching problem, right? But we have to figure out what kind of answers specifically we're trying to get out of this and what our needs for this bioreactor to be. So obviously, we need this to be completely sealed off from the environment, right? In terms of we don't want any outside contaminants getting into the bioreactor, you know, the wrong type of bacteria gets in there, starts the wrong type of degradation process, and all of a sudden, all your data is out of whack. we also kind of don't want stuff getting out. We don't want to be working in a lab that's just slowly filling up with greenhouse gas and carbon dioxide and nobody knows. So we need this to be completely sealed off from the environment for a number of ways. We also need it to be cost effective and be able to be constructed with readily available materials, because again, we're kind of working on this idea of frugal innovation, we were calling it, at the time, and I think that we didn't stop calling that, but that was a big focus of it at the time, was being able to construct this effectively. And so we kind of looked at what pre-made bioreactors are like, and they ranged from $340 for a 1,000 milliliter bioreactor, all the way up to this one on the bottom left is $18,000. So again, we didn't even really have a starting point that we could just buy in and save some work. We really had to go do it ourselves from the very beginning and kind of try and balance the needs of size versus cost. So we also need this to be sturdy, right? This is going to be holding up to, who knows what kind of chemicals and leachates are going to come out of these clothes. And we figured that it would be pretty similar to wastewater, right? That nasty kind of stuff that's coming out of landfills. And, wastewater comes out of sewage pipes as well. So one of the last experimental needs we identified as well was, if we're simulating a biological environment, right? We're trying to simulate an open air landfill. One of the things that landfill is going to be exposed to is not just the air, but also water through rain. So we wanted a way to add a set amount of water at a time so that we could kind of simulate, oh, this area gets X milliliters of rainfall a year. We can add that in at the rate over the year and emulate kind of that rainfall. And we also, on the other hand, need to be able to remove the water. We can't just have this flooding continuously. That's kind of not how the real world works. So we needed to then finally be able to record the internal values as well. No experiment is useful if you're not getting information out of it. All right. So we decided that we wanted to collect the gas produced in terms of volume and in character. And in terms of measuring the water, we wanted to measure it for the pH, dissolved solids, electrical conductivity, which is similar to dissolved solids, presence of heavy metals, and the oxygen demand, biological and chemical. Oxygen demand, pretty simply, the higher oxygen demand, less oxygen is dissolved in the wastewater, and it's just harder for biological life to survive. So it turns out all of these are also super expensive to do, ranging from a couple $100s to a couple $1,000s for just a gas meter. So again, we kind of wanted to do that on our own. In terms of the larger construction of the product, thinking about what is waterproof and airtight, what is cost effective, and what won't degrade under wastewater. Easily modified PVC pipe, ubiquitous in plumbing across every single house in the United States, and it meets all of those kind of necessities. So we have a general guiding principle of how we're going to build this, but now we need to work on lab equipment as well. So how are we going to take those measurements? We floated some ideas in terms of for gas, like liquid displacement, but I had just taken a class that worked using a lot of Arduino messages, or Arduino microcontrollers, and we thought that we could apply that here. And it turned out that that was kind of a great novel experience for us. So we got to work on that. We used sensors for methane concentration, carbon dioxide concentration, pressure, and temperature. So these are just a few of the ones we had. This is for methane, CO2, and pressure and temperature. And drinking water quality tests under EPA standards were used for the rest. And all of that was constructed for less than $150. So now it's time to get into designing and prototyping the actual reactor. But it's January of 2021. We're spread out across the country. And so we decided that we would kind of do this virtual, passing ideas back and forth from each other until we kind of got everything right. We're sharing videos, making presentations, kind of, sending these digital designs for how to use the Arduinos to each other. And this was a great one. This was ThingSpeak. This is what we use to monitor the data online, make sure there's no problems. And so then that's kind of where we're at now, right? Where we're moving from prototyping, like this image on the right, into actually producing these. We're hoping that in a year we can get an idea of what one t-shirt will release in terms of pollutants, and then we can extrapolate that to the larger quantity. It's not going to be a perfect estimate, but just to get the word out, any estimate is better than none. And we're hoping with the modularity of this, you can kind of expand or contract the environments to get an idea of global estimates and local community-wide estimates. And we also did some advocacy work with crossing over between art and design. This is at the McMullen Museum of Art. This is at the Smithsonian in DC. And then another picture from the Smithsonian. And the next step is kind of putting this into the hands of everybody. We made this with affordable materials and fairly simple construction. So we're hoping that anybody can produce one of these bioreactors themselves that they can use to estimate decomposition across environments and materials, for example, food, construction, or plastic waste. And we're hoping that this does a little bit of work to kind of put the ability to do research and kind of learn about the environment and the world around you into the communities who are most impacted by it, not just those in research institutions. So that's it for me. If anybody has questions, I'd be more than happy to answer them. I know I went a little bit over there, so hopefully you guys aren't mad at me.
No, you were right on time, Evan. Thank you so much for sharing that. And I know from my involvement in this project that this has been a really long and winding road for you. So you did a great job of kind of summarizing the key points and what you've learned along the journey. So thank you for sharing that with us. We have just a few minutes for questions before we move into our next section, which will be focused more on innovation, art, and advocacy. But I want to open the floor for anybody who has questions about Evan's work.
Yes, I have a question. Thank you, Evan, for a wonderful presentation. My question would be, looking over this, it seems that it would require many courses in chemistry, biology, and then also a creative mind to put all this together. So my question is, considering how much content and how much design thinking would be required in order to proceed with this, what was the most challenging part that you found about this project?
That's an awesome question. And I think you kind of touched on the answer with one of the first sentences you had there. You said that it seems like it requires so much knowledge across biology and chemistry and engineering and design thinking. And it definitely does. You know, you have to kind of have a little bit of a general knowledge in all those concepts. But I think one of the issues was kind of that imposter syndrome a little bit, right? It feels like you're facing down this huge problem of like, oh, I have to design this entire thing with, you know, me and undergrad and our mentor, you know? And it really was, I'm trying to figure out the words to say this. Getting past that imposter syndrome was kind of like the biggest thing there, knowing that this is a huge problem, but if you have like team members you can rely on, you can get over that and like get a little bit of info from everybody. So we did have like experts across different fields working on it. And also just taking the time to research, you're able to kind of cover those gaps in your own information. You know, nothing here ever really came from absolute scratch. Nothing was ever totally built up from the ground. You're always kind of relying on previous research. So acknowledging that there are things you're not going to know, but that there are ways to figure it out is very powerful and kind of was impactful here, and something that I took over to other, you know, parts of my schooling and life.
Thank you for that question, and thank you, Evan, for your thoughts on that. We're kind of almost out of time, but if there's maybe one more question from the group, we have time to take it. Okay, it looks like we have a question from Kate.
Yeah, you talked a lot about how a big part of the project was making it less expensive, making it more accessible. Can you just talk a little bit more about how you hope, like, if a neighborhood or a community or a class got to build something like this, like what they would do from there, what they can do with this information?
Yeah, definitely. So, I mean, focusing in on that last part first, in terms of like a classroom getting access to this, I think coming from an education background, it really does offer like a fantastic way for kids to kind of learn about the scientific method, like hands-on, right? So you can kind of modify this to whatever experiment your class is going to do. You can modify it by age and kind of let that be their first foray kind of into research and the scientific methods. So kind of getting people interested and aware of how science is performed is kind of a goal there. And then bringing this up, I guess, towards like more communities instead of classrooms. Research, like scientific research, is one of the ways that you can like make change in this world, right? If you learn about something and you kind of get answers about it, then you can create awareness about that. But that's also incredibly expensive. So textile waste comes to mind as kind of this issue where the groups that are most impacted are the ones that globally kind of have been the most silenced because of access to resources. And kind of the group that needs the biggest behavior change, as we've seen in other presentations, the people who need to work on their textile waste recycling habits are the ones that have access to this research. So not everybody is going to have the willpower to, you know, turn the looking glass around on themselves and be like, okay, this is the impact I'm having on the world. Oh man. So we're hoping that by having a more affordable, more easy access into research for a lot of communities, they can kind of, you know, raise awareness about the problems that are facing them on a day-to-day basis. So kind of being able to remove that cost barrier to bringing awareness on the global stage to, you know, research issues like environmental waste or textile waste in the environment.
Great. Thank you so much, Evan, for your presentation and for your responses to those questions. We are going to wrap up our research section on that note. And as a reminder, as I will do after every single presentation, even if people get sick of it, we have this presenter form available. And if you have any feedback, ideas, questions, anything that can like keep the work and conversation going, please use that form to connect with the presenter. And as I mentioned previously in our conference schedule, we also have bios and contact information for everyone who is speaking today at this conference. And so we really encourage you to reach out and connect. And one of our main goals with this conference is to try to bring people together who are maybe doing similar work